Hey Sean, you remember that video that made the rounds on the internet last year from TED about 3D printing?
The clip technology?
From the company Carbon, and it was a video of a piece being printed out of resin that basically looked like it was just coming out of the resin.
Like super speed.
Oh my God, and even though it was time-lapse, I think about 7x, it was much faster than any of the 3D printing technologies we'd seen before.
Yeah, it seemed like black magic.
Right, and well, we are here at Carbon where we're gonna get a demo of their actual machine, the M1 printer.
Yes.
Super excited.
Me too.
Let's go check it out. Hey Kirk, it's great to meet you.
Nice to meet you.
We're very excited about this. So this is it. This is the M1.
Yes, our first product.
Wow, and it uses Carbon 3D's clip technology, which we saw videos of online. Yep. It's gone everywhere. Can you describe a little bit about what's going on, what the machine encompasses, and how it differentiates itself from other printers that use resin?
Sure. So our technology, clip for continuous liquid interface production, is a fundamental advance in 3D printing. And what it allows is for us to print very fast, without layers, in engineering materials. So all that together allows us to work with people who want to make real parts for production, as opposed to just for prototyping.
Right, which you can do also prototyping.
Correct.
So continuous printing, how does that happen? Because we've seen SLA printers where a laser goes by layer,
Right.
and then there's a scrape process, and over time, over many hours, you get an object.
That's right. So SLA, as you know, has existed for 30 years, and it's a great technology for prototyping. Our founder looked at SLA and realized that there was a bug that could be a feature. He realized that you can get rid of layers if you control not only light, but oxygen and light. And up to this point, the SLA industry has thought about oxygen as the enemy. But if you make oxygen your friend, you can remove those layers and go really fast and use a much wider range of polymer chemistries to create these amazing parts.
Oxygen is something that inhibits the curing of
That's
resin.
exactly right. So a light turns your liquid into a solid. Oxygen prevents that from happening. And if you use sophisticated software to modulate the effects of both together, to make them work together, you can make these amazing parts.
So what kind of light are you using?
We're using UV light, and we use the same UV light that's used in other SLA approaches. But again, it's the combination of light and oxygen that allows this magic to happen.
To do it continuously, are you drawing the outline of the print? Is it all going one time?
So underneath, down in the cabinet here, we have what's very similar to a very high performance desktop projector. We're projecting an image. Imagine playing a movie. So we take your three-dimensional structure and we take its cross-section and project its cross-section into the bottom of this liquid vat. Then again, controlling both the light and the oxygen, you can get rid of those layers and make awesome parts.
Right, it's like basically a DLP projector.
That's exactly right.
Because the software still does slicing of traditional
Correct.
models. So you think of like a cross-section, like you
Correct.
said.
Yes.
But instead of drawing the outline or drawing the inlay, it's just projecting that all at once.
Correct. That's right.
Does that also then inform like the bed size?
That's right. So we are launching M1 to get Clip out into the world because we've got engineers and designers and business people who want to use 3D printers to change the products they make and to change the businesses they run, right? Imagine you want to get rid of your spare parts warehouse, all these plastic parts just hanging out waiting for someone to need a spare part for your 2006 Toyota Matrix, which is the car that I drive. Right. That's a bummer to have to hold all those spare parts in inventory waiting for Kirk to call when he needs a new door handle, which is a problem I had just this morning. So instead what you want to do is you want to have a production quality 3D printer that can make that part at an appropriate quality for me to use in my real life. So that's what this machine is about. And we're really excited to show it to you today.
Yeah, and I think the best way to illustrate it is to actually get the demo.
Let's
so let's start this. And the resin I think you have going here is your prototyping resin.
That's right.
The fastest printing one.
So we have a wide range of resins, some of which are for final parts and some of which are for prototyping. Now, as you know, when people are making real things, they go from concept, an idea, to a final product. And along that process, there are many different resins you might want. You might want to prototype first, then understand the model and its geometry. Then you want to go to production in a high quality engineering resin. So what's happening right now, this is the build platform and it's descending into this liquid puddle of resin. The light, when we get down here into the bottom, will project into the bottom of this pool of resin. You can think about this as a small fishbowl. It's a container of liquid with a transparent bottom surface. We're going to project through that transparent bottom surface, and we're also going to, with our physics and chemistry model, control the oxygen and its interplay with light. So now you can see that the build platform has descended into the pool, and you can't see this, but underneath we have our optimized projection system with UV light projecting into the bottom, projecting the cross sections in as we build the object. So the object is being built right now, you just can't see it because it's underneath the surface of your pond of resin.
So Kirk, this is super exciting, and this whole process with this model and this material is going to take about 15 minutes, you said. So
That's right.
I'd love to use that time to ask you more questions about the technology outside.
Great, let's do it.
All right, Kirk, so I'm still trying to wrap my head around just how the clip process works, because we're seeing it working in real time, and it really is coming right out of that pool of resin.
Right.
Can we start just at the base of the machine? So there's a way you're curing resin with light, UV light, and it's coming out of what's essentially like what you said, like a TV, like a movie projector,
right?
Like a DLP projector,
right?
But through UV light.
Yeah.
Now, when I think about that, and that comparing to like a laser drawing each of the lines, is there a focus point where? How do you get an even distribution, I guess, of detail?
Right. Well, so the answer is with great engineering. So we live at the intersection of hardware, software, and molecular science, and we have some amazing engineers here. And because we knew we were building a machine for production purposes, we knew we had to have great performance over the entire build area. So we hired some amazing engineers from the photolithography industry that makes chip making equipment for people like KLA Tencor and Applied Materials. So there are engineers out there in the world who know how to take digital projection systems and make amazingly high quality optics to go around them. So we use a custom high performance projection system as the source of light that we use, again, in combination with oxygen, and that's the critical thing. Light and oxygen working together to remove the layers from the parts so that we can go really fast and so that we can have incredibly high quality and use these engineering materials that are appropriate for final use parts.
With you're constantly developing optics and you're using a custom projection system. Do you envision bigger build sizes?
Absolutely. So when we work with Fortune 500 manufacturers and they see this amazing quality and they start to think about what that could do for their businesses, from changing the way spare parts are fulfilled, so you don't have to keep your spare parts in the warehouse, to changing the type of thing you can make. So light and strong meshes for electric cars or to increase the safety of conventional cars. They're really excited. They want to make the parts that are going to change their business, change their product. And of course, there are a ton of parts that fit within our existing build platform today, like this, like that. But they have some larger parts as well. And we are working with those partners on the next generation of clip technology and the new products that will embody that next generation of technology.
And so important to that clip technology is that oxygen permeability, combining oxygen and light. And that happens in moving up from the machine, the cartridge. So this is an example of the cartridge where that resin was sitting on here.
Correct.
And you have a proprietary, that material is where the magic happens.
It's the combination of the hardware, the software, and the chemistry that allow us to control both light and oxygen in a very subtle and complicated way to get rid of these layers. Like I mentioned to you, we have a very complex physical and chemical model running behind the scenes that controls the printer and makes sure that light and oxygen are appropriately balanced to make these amazing parts.
You're controlling light, but how are you controlling the oxygen?
As we talked about before, I can't get into the details of how we control it. What I will say is that we understand, as you saw from the science paper, the physics and chemistry of light and oxygen together and how they work with the chemistry, with the software, with the hardware to balance these effects and make these great parts.
In some of the SLA printers we've seen, that layer where the resin sits in over time gets clouded, and the cartridge itself, the tray, is a renewable. You have to replace that. Is that also the case with carbon?
So this tray is removable. It's mostly removable because our customers want to run these printers all the time. So imagine you want to switch from one resin to the other. You've got resin A in the first bowl and resin B in the second bowl. You want to switch. You want to go from rigid to elastomeric. Like this material people love because it's like a production elastomer, right? So athletic footwear companies are really excited about this because it matches the performance characteristics of your midsoles, which is very unusual. No one else in the industry has ever done anything like that. So imagine you want to be printing something rigid like this for a jacuzzi at one point, and then you want to switch to making something elastomeric for a gasket, for instance. We make that easy by allowing you to just switch the cartridges in and out. Now you asked about the
clouding.
Right.
And, yeah.
We've been working with, like I said, we have a number of Fortune 50 partners who have been running these machines day and night. We've never seen any clouding.
Wow. So long-term use
Yes.
is, and that's a testament to the system. And then the resins itself, you alluded to that. I mean, there's so many different types of things you can print here.
Right.
You know, what's the range and the strength of the resin?
Right. Well, I think the easiest way to kind of give a sense for why we're so excited to come into work and why we think clip is such a transformational technology is to talk about some parts. So one part that's particularly interested in me, I'll talk about the material. So this material is our cyanide ester. It's equivalent, it has a mechanical properties equivalent to 15% glass-filled nylon, which is a very commonly used engineering resin that's tough and strong. This resin also can go up to 500 degrees Fahrenheit with no change in properties. So one company we're working with that we're really proud to be working with because their story is so inspirational is a startup called Nativis. And Nativis is founded by a ex-Navy veteran who worked on engineering systems there. And he knew that there are very high-performance compressor systems that are also very energy efficient. And they rely on compressor elements like this one. Prior to carbon 3D technology, the only way to make this shape that could survive in the heat of a compressor was to take steel and CNC it in a multi-axis CNC machine.
Yep.
As a result, this component was really expensive. So high-performance compressors were also very expensive. When he discovered carbon technology, we printed that geometry for him very fast and much more economically. And what that allows him to do is take this previous military technology that was very good at what it does, very expensive, and use it to create very economical in-window air conditioning units for India and China.
Right.
So when we get up to, come to work in the morning, it's really inspirational to think we're allowing air conditioning to be way more efficient, energy efficient, and way more affordable for people all over the world. And it's enabled by this sort of material and clip technology.
The ability to use materials that are closer to what people actually use in manufacturing, whether it's for casting resins, it's not just the material that's solely 3D printing. And
Right, exactly. So our multi-stage cure, we talked a lot about clip and the balance between light and oxygen. That was core innovation number one. But as important was what that clip allowed you to do this two-stage process where we set the shape with light and oxygen, but we set the mechanical properties with chemistry. And that's a fundamental change from the way that 3D printing has been practiced before.
Yeah, because previously you take a shape out and that's it. That's all you can do
Correct.
with it.
Light-
Maybe you bake it to make it stronger, but
Exactly. Light was setting both the shape and the chemistry. So you can imagine if you tell a chemist you can only use light, you've got a limited set of things you can do. And that's why existing SLA resins have the limitations they do. But if you say, I'm going to free you from those constraints, and you can use light and oxygen to craft the shape, but you can use a universe of existing thermoset chemistries that already have been developed for engineering applications in reaction injection molding, in urethane casting. Now you open up a huge range of future opportunities, whether it be the elastomer, the rigid polyurethane, which performs, I believe, better than ABS in many cases, and you can see the stress strain curves on our website, to cyanide esters that are equivalent to glass-filled nylon. I mean, this is mind-blowing for people, and it enables a whole new range of products and businesses to exist.
So you're also using two-part resins.
Exactly. So again, the core innovation of clip is about the balancing of light and oxygen, but there's an additional innovation that is critical to getting these great parts, these great mechanical properties, and it's two-stage cure. So stage one, we take these two-part resins, we put them in the printer. We then craft their shape with light and oxygen, and then we set the mechanical properties with chemistry. And that additional degree of freedom gives us a much wider range of possibility, and it's part of why our manufacturing partners are so excited to be working with us.
Yeah, I know for like urethane casting, often you pour two resins in, you have a work time of maybe 5 hours, 5 to 8 hours, and if you think of a big complicated print on a traditional printer, you can't use that resin.
Exactly.
Because it would need to be multiple days of printing.
If your print takes 36 hours, you're at a disadvantage. What you want to use is these reactive chemistries that access these great mechanical properties, allow you to make things that can be sterilizable for medical applications or live under the hood in automotive or aerospace applications.
Now, with the increased complexity with chemistry, you're also introducing things like exothermic reactions.
Yes.
The prints can get hot as you're printing. How does that change the print process, and how do you compensate for that?
I love it that you're so informed on the chemistry side. This is like we mentioned, we live at the intersection of hardware, software, and molecular science. So we live this intersection, and you're totally right. When you use light and oxygen together, you create a reaction. That reaction releases heat. Luckily, we have what I believe to be the best chemistry team of any 3D printer company, and we think a lot about these the details of how you balance the physics and chemistry to make great parts. And in the future, we believe, as we print even faster, heat will become our friend. If you think about chemical reactors and how engineering resins are made in the supply chain, it's all about pressure and heat, right? And those chemical engineers understand those constraints and engineer to use them to their advantage. We'll be doing similar things, and it's a really exciting prospect for the future of clip.
How does it change how designers, if you're working in CAD or designing and you've worked with other types of printers, how does it change how they think about printing objects, just for things like overhangs? Can you print structurally so you don't need lateral supports?
Yeah. So I'd say the first thing is, with an existing technology, if your printer is only good for prototyping, you're in a rough spot as a designer because you think, okay, I've got to make something that can ultimately be injection moldable. So when you go to the printer and there are optimizations, things that this printer can do that are better for you as a designer, you can't necessarily take advantage of them because you're thinking 2 steps down the road, and you have to be compatible with injection molding when you get there in your design and development process. But when you have a printer that can make final quality parts that are appropriate for shipping to your customers, you are freed of that constraint, and you can use the benefits of 3D printing, right? You can make lattice structures, you can make customized products. And that's part of what's changing when we deliver this sort of product to customers, because they've been freed. They don't have to think, I've got to make an injection molding design, work on this 3D printer for now so that I can move to injection molding.
Does the economics work when you're talking about leasing a machine and being able to print even so fast as you can do right now? Does that work for businesses?
It does. So as I've mentioned, we have printers in the field with Fortune 50 manufacturers, and their intent is manufacturing. So the first question they ask is, does this work for my business model?
Yeah.
And from automotive to aerospace to medical to consumer products, the answer has been yes. So when we founded the company and we said the goal is to make a manufacturing grade 3D printer, that's as much about business model as it is about technology, right? If we want to deliver on this promise, we can't just say, here's a great technology and it's astronomically expensive. We need to say, we understand the realities of your business, and this technology allows you to run your business in the way that you want to. So we have a number of people, particularly on my team, who think a lot about how do we scale up, who are we economical for today, and how do we continue to push the limits so that we can make this technology as widespread as possible.
Only it's going to get cheaper, faster, and more versatile.
Exactly.
As a technology.
And again, getting back to our materials advantage, because we're using existing engineering thermosets, we get to use the existing engineering thermoset supply chain that's already scaled up for mass production applications, right? They're already selling polyurethane that's used in real objects that you interact with in your everyday life. So we can go to that same supply chain and we can go, guess what? Bring your awesome chemistry into the future. Put it on this amazing new technology, and we'll make things we couldn't make before.
And then don't have to worry about long-term reliability because it's proven materials.
Right, exactly. That's why we can pass these stringent reliability tests that the automakers have, because we're using engineering-grade materials. These reliability tests that we're seeing coming in where we see no change in properties after 100,000 or 200,000 or 300,000 cycles. Our collaboration with BMW that we've been public about, where we have nameplates on the outside of cars in Berlin, going through the temperature cycling, going through the wear and weather and things bumping into them. I'm not aware of any 3D printer that's ever produced a cosmetic final quality part that's survived through the rigors of real world application.
Yeah. Cosmetics just one area.
To be a consumer product, you got to look great, but you also got to be super tough, and you got to be produced at an appropriate cost so that it can actually make sense for an automaker's business. And we've got all of this with Clip, which is great.
That print that we got a demo, I'm sure it's almost done now. What's the finishing process like once it's out of the printer?
So as we mentioned, we have a two-stage process. So you build the object in a liquid. So there's a wash step to get the extra liquid off of the surface of the part. Then, so we've set the shape at this point. What we're then going to do is put that object into an oven. Remember, because we set the shape with light and oxygen, and we set the mechanical properties with chemistry, with heat. So we're going to take that object, we're going to put it in an oven, we're going to kick off that secondary thermoset reaction and give it these amazing mechanical properties that allow you to be like glass-filled nylon and resist temperature up to 500 degrees Fahrenheit.
Super, super exciting. Thank you so much, Kirk.
No problem.
For sharing with
Thank
us
you.
the clip technology at Carbon, and I'm sure we'll be hearing a lot more from companies soon. Thank you so much.
No problem. Thank you.
Wow, look at that.
It's the future, Norm. It's the future.
That printed in about 16 minutes,
Yes.
which is incredible.
It is, and it's very fine resolution. It was very impressive. We saw the videos on the internet, and you're like, well, it's sped up, whatever. But you really could see this emerge from the vat as we watched it.
In
I
real
was really
time.
surprised.
Right, even after just like 3 or 4 minutes, that
Yeah.
build platform was coming out of the pool, and it was unlike any 3D printing technology
Absolutely.
we'd seen, at least on the home and consumer side. Now, to be fair, this is with their prototype resin.
Yes.
And this is like the kind of the best case scenario. They're printing something that, while geometrically is complex, it's not a huge amount of surface area per each
Sure,
of
and this
their-
isn't going to
their
go into a
slices.
working machine or anything like that. Because that's the one thing I think we kind of discovered on this trip, that they have the 1 and 2 part resins, which I did not know before.
Right.
And there is a difference in curing times depending on which ones you're using. So, but this is still very strong, and the resolution is very, very fine.
Right, the demo we got really was illustrative of that whole oxygen permeable layer. The
Yes.
idea that in an SLA printer, you're talking about the laser draws, like the form printer, for example, the laser draws each layer or each slice, then on the tray, it swipes.
Yes, which is where this might run to a bit of a problem because it is so fine, but because it's just emerging out of that tray.
They're using oxygen as a way
As-
to detach the
Yeah.
resin, the cured resin, from the pool of resin.
Yes.
Now, they also told us that the print times, what's actually going to add to the print time, if you have a complex shape, is the resin pool actually filling back in.
Yeah.
Right?
Yes.
And so in a traditional SLA printer where there is a swipe, that swipe brings the resin back in to cover the surface area. Here, because it's just oxygen, you're allowing gravity to pull that resin back in.
Exactly, yes. So there are some variables, but overall, very impressive technology. And the prints that we saw, they were really quality prints.
I mean, things that are put directly into production. You talk
Yes.
about cars, right? Cosmetic things for cars. What I love is that we also got to see a bike pedal, and they tapped hardware into the
Right
bike.
into it.
Which, if you think about it, if you try to drill a bit into a 3D print, it just shatters.
Typically, yes.
Yeah.
And the other thing that I was curious about was this is UV cured resin, both whether you're talking about SLA or DLP or the clip technology, it is all UV cured. And a lot of those prints, I always tell somebody when I give somebody a scuttlefish or something off, the other printers, don't let this sit in the sun. It's UV sensitive, or
It'll
give it
get
a
brittle,
or paint it,
it'll discolor.
Right, it could discolor, brittle, and they're using engineering quality polymers on some of their higher end resins, which they're heat resistant and UV resistant, and they can be put into service in high temperature environments. It was really impressive.
And it's the same polymers that companies have already been using
Yes.
outside of 3D printing, which means it's proven.
Yes.
What the real big takeaway is that this machine, it's not for you and me, right? They're selling it, they're leasing it to companies for about $40,000. Companies like Sculpio, who then can sell services, print services to consumers, but it's really for high-end manufacturing, at least
Yes.
right now.
Yes.
So it's going to be a while before, hopefully this technology will get cheaper, will get faster, will get more versatile.
I would love to see this on our desktop.
That is the dream.
I know.
Well, thank you to Carbon for giving us a preview into that future. I'm walking away gobsmacked because that's a beautiful, beautiful print. This is an awesome trip.
Yeah, absolutely.
And with more stuff like this on Tested, please subscribe to our YouTube channel. Sean and I will see you next time.